Good morning, everyone. Welcome to EasyPower Thursday webinar. My name is Jim Chastain. I'm Applications Engineer with EasyPower. Today, before I introduce our guest speakers, we would like to conduct a real brief opinion poll. Gather some feedback, if you would please participate. And again, we welcome your participation and feedback. So the first question is, are you aware that the IEEE 1584 standard has been updated? And again, there's no obligation here, and we're not trying to put anybody on the spot, just to kind of get some feedback on the perspective that people are bringing to the table today. As we're collecting feedback, I wanted to mention that normally we schedule this presentation for 60 minutes. The material is rather meaty, and there's a good chance that we're going to overrun that time schedule. So apologies if it's not fitting into your schedule. The full webinar will be recorded and will be on our website, along with a PDF copy of the slides. So you won't miss anything if you have to leave early. So it looks like we have a quorum here on our responses. I'm going to close this and share the results. We have fairly good representation of folks that are aware. Good. And so just out of curiosity, have you started using the new models that are represented in the 1584 changes? So here's how the responses came in. At this point in time, I'd like to hand the baton over to our guest speakers from ABB, Mr. Samy Faried, our first presenter. I'll let them introduce themselves.
Thank you so much for sharing your time with me. My name is Samy Faried. I'm a Regional Business Development Manager, and I'm also a Field Application Engineer at ABB. I have over 30 years of experience in electrical power system analysis, engineering, design. I have 3 degrees in electrical engineering. I also taught at 6 different universities, and I'm delighted that I'm sharing my experience with you today.
Thank you very much, everybody. Good morning, good afternoon, good evening, everyone. Thank you for attending. My name is Ryan Bergeron, Education with a Master's in Science and Electrical Engineering, MBA, as well as Samy, hold a senior membership status with IEEE. I joined ABB in July of 2018 and worked for ABB's Electrification Business Industrial Solutions equipment line. Based out of Minneapolis, Minnesota, founder and chair of IEEE Twin Cities, Foreign Energy Society, as well as Industry Applications Society. Samy and I will supersede the webinar that I completed with Jim Chastain 1 year ago, titled Understanding NEC 240.67 2017 Arc Energy Reduction for Fuses. And the reason why we are here today is that electrical safety is important to electrical engineering and is ever still present or ubiquitous everywhere there is electricity in the world. The goal of this updated presentation is to educate and reduce the electrical incidents and fatalities. There is a need for this now. IEEE stands for the Institute of Electrical and Electronics Engineers and is a trusted voice for engineering, computing, and technology for information around the globe, which was formed in 1963. The agenda for today, we will understand the new IEEE 1584 2018 guide, NFPA 70E, as well as OSHA. So Samy will begin portion number 1, as well as help you understand IEEE 1584 for the new inputs for the 2018 model, working distance, electrode gap, electrode orientations, as well as the size information. There are multiple and varying arcing currents associated with IEEE 1584 2018. Next, myself, Ryan Bergeron, will review fuse clearing time problems with the 2017 NEC 240.67 article. Case number 1 will review varying cable lengths, and in case number 2, we will discuss it in 5 parts for varying transformer sizes. Parts 1 through 4 will have a 24-inch working distance and will show you the associated new results from the EasyPower software program. In part 5, again, talking about varying transformer sizes, what happens when you have an 18-inch working distance result? We'll show you what that means for fuse clearing time problems. Third, Again, myself, Ryan Bergeron, will go into the EasyPower 15 kV and below modeling solutions for the new and retrofit applications. We'll review arc energy reduction solutions for the new 2017 NEC 240.67 article in 4 parts: Part B, B1, B2, as well as B3. I will also perform a live model with EasyPower 10.2.0.108 with the IEEE 1584 2018 installations. And then Samy will help you understand some final application considerations, as well as understand the present and pending enforcement maps of the 2017 NEC 240.67 article. Nearly 130 years ago, in 1890, Thomas Edison invented the first fuse and served as a safety over current protection device. The I2T rating is related to the amount of energy let through by the fuse element, as it clears electrical bolted faults very well. Over time, larger fuses were created as more power was required in today's world, and an effort was created to understand the hazards associated with the arc flash phenomenon. Thus, IEEE 1584 was created as the first guide. We now know for certainty that the initial guide had limitations. In addition, several versions of the NEC have been introduced and adopted to legally enforce methods for various technologies for electrical safety. Recently, the NFPA, National Fire Protection Association, partnered with the IEEE 1584 Working Group to improve the science of the arc flash calculations. Thus, IEEE 1584 2018 was approved on September 27, 2018, and available for public download on November 30th, 2018. EasyPower offered their first new software for public download with the new IEEE 1584 2018 equations on February 1st, 2019. So it has been about just 3 months into the process of beginning to understand the changes. IEEE 1584 is the IEEE Standards Association most widely circulated global standard sponsored by the IASPCIC, or Industry Application Society Petroleum and Chemical Industry Committee. This presentation on helping you understand the IEEE 1584 guide will offer a new paradigm towards making informed and safer decisions through electrical engineering facts, reviewing of new data, and determine cost-effective arc flash mitigation solutions. Now, please allow me to shift the presentation to Samy.
Thank you, Ryan. Hello, everyone. Again, good morning, good afternoon, good evening, depending wherever you are. Thank you again so much for sharing this time with me. Allow me to explain in simple terms what's arc flash. IEEE, there are 3 main regulating body for the arc flash calculations and safety precautions that we have to take. IEEE 1584 essentially lay down the formulas to calculate the calories per centimeter square, which is the level of hazard that this system is going to provide and can be extremely harmful, if not fatal, to the operator. NFPA 70E is a standard that was written in cooperation with OSHA. OSHA is the federal regulating body, and the last production is what we call final rule, and it was produced in 2014. OSHA essentially tells you what to do. NFPA 70E take that what to do and translate it into how do I do it. And then 1584 guide will actually give you the formulas needed to calculate the value of calories per centimeter square. As I'm sure you know that the magic number here is 1.2 calories per centimeter square, because that's capable of causing a second-degree burn. Let's understand the fundamentals of arc flash. Arc flash happens 5 to 10 times daily in the United States. And in order for us to understand it, the most simplified way, imagine your hand or palm on top of a candlelight. The candlelight intensity is related to the short circuit or bolted fault value of short circuit current that a specific system can produce. The hand itself, the movement of the hand is related to the speed of the circuit breaker, relaying system, and also how fast the fuses can trip. To give you an example, a 3-cycle circuit breaker would take 50 milliseconds to trip. But if we look at this picture, the faster the hand is going to move on top of the flame, the less damage is going to happen to the skin of the hand. So as we try to calculate the incident energy, which how many calories per centimeter square is going to penetrate the palm, those are all empirical formulas, which means we are approximating the value of calories per centimeter square that a specific system is producing. And as you will notice shortly, we used to deal with about 3 pages of formulas in the old system. In the 2002 edition, now we have more than 17 pages of formula. But please remember that these are empirical formulas. These are not accurate formula. If you want to exactly know what's the arc energy, please look at the bottom of this page. Arc energy, which is the energy inside this arc flash, consists of 3 components: volts times amps times time. And volts can be controlled, amps can be controlled, also time can be controlled. A time essentially related to the speed of movement of the hand or the protective system that is being used in this system. Please remember this bottom line equation, because it is accurate equation, and I'm going to use it to illustrate how do I mitigate arc flash. Okay, NFPA 70E was done in cooperation with OSHA. And by the way, OSHA is our federal regulator, and OSHA's policy is to adopt any realistic standards that are being produced in the United States. Like, for example, it adopts NFPA 70E, and also it adopts IEEE 1584. The best way to avoid arc flash hazard is eliminate the hazard itself, which essentially mean make sure it's disconnected, it's de-energized. And by de-energized, please be aware of the fact that you have to make sure that the voltage is 0, because as you know, there are capacitive components of the electrical system that can store energy. So when we say de-energized, we mean voltage 0. The second approach is substitution. Replace the hazard in the design area. I mean, while you're designing the transformer impedances, cable impedances, distances, relays, protective system, be aware of the hazard and take whatever measures you need, because you're going to have a choice at that time when you're designing the system. Then we proceed to engineering controls. The system is already established. I have an existing system. What do I do about it? And this is essentially going to be explained further by Ryan. What steps do I take and what devices do I use to make sure I minimize the arc flash hazard? Awareness is a huge factor here. Safety training is required by OSHA every 3 years, and this is one of the most effective ways of protecting people, because when you are aware that this is not really a casual hazard, this is a life or death. Administrative control is a lower level precautions or steps which encompasses making sure that people have procedure to tackle a specific operation, observing steps, being aware of which steps can cause danger or hazard to the people. And finally, the least important is PPE, which is personal protective equipment. Personal protective equipment are 4 categories, and they are based on a specific value of calories per centimeter square, and but ultimately awareness of the hazard, being aware of the site condition is the most important thing, and experience in this area is extremely crucial to protect people. Okay, now we go into the details of what's happening with 1584. The previous model, the 2002 model, had 3 pages of formulas. When we switch into the 2018, those 3 pages translate into 17 pages of formula. Obviously, a serious problem. There are coefficients, there are new parameters, there are concentration, how the buses are oriented, and as you know, the more input we put, the more the chances of error appear. So be extremely careful with the beginning assumptions, how to describe your system and the data collection process. Okay, to give you just a quick look at the new formulas. I'm having a hard time reading it myself because it's printed here, but as you see, it's quite complicated, and that's what's included in the 1584-2 model. Let me summarize for you the main differences between 1584 and the 2 model and the 2002 model. Okay, in the old model, which is the 2002, the version 1, we accounted for gap between electrodes, working distance, how far am I from it, operating voltage, bolted fault, which is short circuit current, and if you remember, that's related to the intensity of the flame of the candle, grounding, and are the electrodes contained inside a box or no. When we switch into the new model, a big difference was electrode orientation. And to simplify understanding this, imagine three electrodes pointing at you, and 3 electrodes parallel to your body. As you standing, the electrodes can be pointing to your face and chest, which is the most dangerous situation, or they are parallel to your body, and therefore the plasma is going to shoot upward. Then the second factor we are accounting for is electrode environments. Are there barriers installed in a switchgear or a motor control center or in a substation that can impede the ejection of the plasma towards me? Box size consideration, that has to do if the electrodes are enclosed in a box, and therefore it will act like a cannon, which is essentially shooting the plasma against me. And then we have more variables with gap consideration. What's the distance between different electrodes? And as you noticed, a lot of extra inputs that we didn't have before comes with inputs, chances of error and inaccuracies in the value of incident energy. The steps of calculating the incident energy, as usual, we evaluate the bolted fault, short circuit, and then from which we calculate the arcing current, and in turn we evaluate the incident energy and how far or the approach arc flash boundaries. Okay, electrode configuration is the biggest change. And if you look at the bottom of this page, the lower half, you'll find the black ones are the old electrode orientation that we have, and the red ones are what's been added to accommodate or to result in more accurate results. We had vertical electrodes inside a metal box, and then that got modified also to vertical electrode terminated in a barrier. And then we have the most dangerous situation, which is horizontal electrodes inside a metal box pointing to the worker face and chest. And the new addition is the old item we had evaluated before was vertical electrodes in open air, and the new addition was horizontal electrodes in open air. Those are the 5 electrode configurations that we have to account for and input to the software to calculate the incident energy. Please observe the 2 illustrations to your right-hand side. When you see the electrodes are pointing to the face and chest, as you know, Lorentz force will push the plasma towards the face and the chest of the worker, and that's what we're referring to as horizontal electrodes, and that represent the most dangerous situation. If you look at the left of this, the electrodes are in a vertical configuration. Of course, you are not out of danger. However, it's not pointing to your face and chest, and all of these factors you have to account for in evaluating the arc flash incident energy. Please remember, all of these are empirical formulas, and the value is approximate, and I will be sharing with you after Ryan's presentation a very, very effective technology to combat the arc flash and result in the most safe working conditions, not only the most safe working conditions, but also minimizing damage to the equipment and also minimizing outages. Ryan, I'm going to hand the baton to you, and please go ahead.
Okay, thank you very much, Samy. At this time, I will encourage you to grab your 2017 NEC National Electrical Code book, as well as turn to the 240.67 article and review page 161 as well as 162 with me. Let's look at the problem with fuses in these specific cases, reviewing the fuse time clearing problems as associated with the 2017 NEC 240.67 article. Case number 1, varying cable lengths with current limiting fuses. The manufacturer should be consulted to confirm the appropriateness of these new empirical and very complicated equations shown at the bottom left for the arcing current clearing time. In this specific example, I've actually modeled this with an EasyPower, but what I'm doing here is utilizing the 1200 amp fuse. It's the same 1200 amp fuse I'm using in 5 different scenarios. I'm specifying an A4BQ current limiting fuse at 1200 amps. The only thing I'm changing is the cable runs and the cable length. If you see on the top portion of this, this is the output from EasyPower, modeling a 300 foot, 600, 900, 1200, as well as a 1500 foot cable run. This was computed in the VCB electrode orientation. If you take a look on the right-hand side, you see the corresponding incident energy at 2.7 for the 1200 amp current limiting fuse at a cable length of 300 feet. And notice the arrow as I'm putting that towards the center of the slide, making sure that my numbers match from 2.7 up to 2.7. And taking a look off to the right, you see the same type of current limiting fuse as a cable length of 1200 feet. And it has a 14.4 calorie per centimeter squared arc flash label, which I am computing here, with a current clearing time of 0.489 seconds. With the development of the new empirical formulas, a special model for current limiting fuses in Annex H of the IEEE 50E4 guide was developed, and there are relationships among arc energy, incident energy, and arc duration. Take a look at the bottom left-hand portion of this slide. T is the arc duration in milliseconds, labeled here. As Samy Faried mentioned before, time is the same included in the basic equation, voltage times current times the time, and time has a linear effect on the incident energy. Take a look at what would be allowable as a method for the 240.67 code. There are methods that meet this and methods that do not meet this on this slide. The areas shown in green are specific methods where a fuse would clear. So in this case, a 900 foot cable run or less would meet a method in the 240.67 version of the code. If you have a 1200 foot cable run in this scenario with a specific type of a current limiting fuse, it would not meet the intention of the code. So it does not comply with a approved method in order to meet this specific version of the code. Now that we have a fundamental understanding that there is at least one problem with current limiting class L fuses, let's understand bolted versus arcing faults, and let's review bolted faults first. For the bolted fault background, this is the worst case fault magnitude, and there are 4 types: 3-phase bolted faults, bolted line-to-line faults, line-to-line to ground faults, as well as line-to-ground faults. If you have solid connections within switchgear and switchboards, which are built for the worst case bolted fault magnitude, this is why equipment manufacturers sell 65 kA, 100 kA, or 200 kA rated switchgear and switchboards in the case of equipment experiencing a bolted fault. If it does, then you can reuse it. Let's take a look at a baseline example of what a bolted fault would look like for medium voltage. Here we will utilize the 1584-2018 14.3 kV empirical formula, which is one of the new formulas for the $4.5 million of investment from industry, as nearly 2,000 tests in high-power laboratories across the U.S. were completed. Here, we are modeling a 13.8 kV switch. The specific dimensions are listed on the left as well as at the bottom of the slide, noted in yellow. On the top, if you can see with my mouse, here is the individual values as well as the windows from the EasyPower short circuit options. You go into arc flash hazard, you pull the pull down menu, you'll see 1584-2002, as well as the specific scenario I have pasted in here. Now, 2018, something similar. I'm pasting these individual values as well as these scenarios 3 times. So in this slide, I'm running 4 different cases. It is more work, but at the same time, we will compare 2002 to 2018. So looking at the outputs, a bolted fault is a bolted fault, as previously discussed. The values for 8.628 are represented here with a dashed line added off to the right-hand side. In 2018, there's no change. 8.628 is the same, and I'm just labeling it right here. So let's go back to 2002. Let's calculate what the arcing fault would be. Based upon the individual scenario that I've performed, 8.395 or 97%, which is the thin gray line right over here. Now take a look at the output for 2018. Is that the arcing faults are labeled at 7.988, 8.126, as well as 7.78. So taking a look at this, 2002 calculated a bolted fault as well as an arcing fault at 97%, but notice what happens here to the arcing faults for this specific 13.8 kV application. There are lower arcing faults with this specific sizing. Taking a look at what's taken on the right-hand side, you have your bolted fault on the right-hand side, and then you have the specific 2002 arcing level current as well as the 2018 varying arcing currents associated with the new model. It is more complicated, but at the same time, it helps you understand where these new empirical formulas are calculating the arc flash incident energy. Again, this is a collaborative effort between IEEE and the NFPA National Fire Protection Association to improve the science of the calculations. Now let's understand arcing faults. Arcing faults, as well as bolted faults, are not the same. When you have 4 different types, 3-phase, line-to-line, line-to-ground, as well as line-to-line-to-ground, you have a potential load side arcing fault noted in the middle of this slide. There is several reasons, such as human factors, foreign objects such as wrenches or creatures that could potentially get into the equipment, or if there are electrical wire or cable insulation failures, this could happen as well. There is no standard for serviceability after an arcing fault. Current is flowing over air, and air is acting as the insulator. From the NFPA research, page 99, table 8A, non-home fires involving electrical distribution, it lists wiring and related equipment as 59% of electrical fires during this 2010 to 2014 time period, which is why we listed electrical wire and cable insulation as a reason for arcing faults. An arc can propagate inside the sections, and the chances of an arc occurring are much greater with human interaction, which has led to the 240.67 code enforcement. So it is not a matter of if an arcing fault will occur, but more so when an arcing fault will occur in unprotected equipment. Taking a look at a 480 kV example, this 0.48 kV fuse switchboard with a 3000 amp main fuse switch on the left-hand side, similar to medium voltage. Now we're applying it to low voltage. Here, again, we're labeling 2002 versus 2018 at the bottom. Notice I've pasted all 4 scenarios within this slide. So let's begin to understand bolt defaults and arcing faults 2002 versus 2018. Bolt default is at 58.196. In 2002, the arcing current was calculated at 23.21 or 40%. And in 2018, with this yellow box, the arcing faults were at 28.868, 33.474, as well as 28.085. So in summary, taking a look at this, is that 2002 calculated the arcing current at 40%, as well as 2018, it pushed the intensity off to the right. Within a time current curve, time is off to the left, and the current is at the bottom. It has pushed this, and it is more intense. And in fuses, it actually lowers the arc flash incident energy with this specific scenario. Notice that the clearing times are labeled here, and I'll talk about that, how it affects, you see me talking about cable lengths, we'll talk about how it affects transformers in just a moment. Again, notice that for fuses, it has pushed it off to the right. Taking a look at the 1584 document, it is intended to provide guidance for the calculation of the arcing current, incident energy, as well as the arc flash boundaries. So taking a look at the bigger picture about class L fuses per the 1584-2018 document, even lower level of arcing faults exist at 208 kV at 106 Ka, potentially low as 20% based upon the testing conditions. For a bolted fault above 106 Ka, the consultant is to contact the manufacturer for more information, as the 1584-2018 guide did not extend testing beyond 106 Ka. Turning towards incident energy, as Samy mentioned before, a value of 1.2 calories per centimeter squared results in a second-degree burn to bare skin. 8 calories per centimeter squared results in a third-degree burn, and you can obtain more information online about this. Finally, looking at the summary of this slide, the higher level arcing currents are shown here. So the dashed line for the bolt default is off to the right. 2002 calculated the arcing current at 40%, as well as 2018 with the transparent red line in the center. Let's take a look at varying transformer sizes. These will be performed in 5 parts, but let's begin with case number 2. With transformer sizes, 24-inch working distance, 1000 kV transformer, listing my assumptions on this slide. Again, pasting the individual values for VCB, VCBB, as well as HCB. The bus voltage fault is calculated at 53.424 in all 3 scenarios. The arcing fault is calculated at 31.648, 36.312, as well as 31.246. Label on the right-hand side. Incident energy, if you're familiar with how EasyPower outputs the menus as well as everything that you're looking at, take a look at the top. If you're understanding the time current curve, take a look off to the right. Or if you understand incident energy labels, please look at the bottom. VCB calculates incident energy at 0.4 calories per centimeter squared. VCBB calculates it at 0.6. HCB is at 0.9 calories per centimeter squared. Like Samy mentioned before, VCBB as well as HCB were not included in the limited 2002 model. Notice how much the incident energy has increased compared to VCB as well as HCB. For this scenario, taking a look at when these type of a current limiting fuse at 1400 amp takes a look at protects this transformer, it clears instantaneously. Bolt default off to the right, the varying level arcing currents associated here, as well as where the fuse clears it. Now, EasyPower does not go at the present time below 0.01, but this is where all fault current ranges need to be considered, which is the way that EasyPower calculates this. So let's move on to case number 2 in part 2. The only thing I'm changing with this scenario is varying the transformer size. So instead of 1000 kVA, I have a 1500 kVA transformer. Same thing, arcing current method for 2004, 1584-2018 method. Taking a look at the arc flash hazard tab in the pull-down menu. The bolt default is at 58.038 in all 3 cases. Arcing fault 28.834, 33.43, as well as 28.05. Now, like I mentioned before, what we have already discussed is that you have varying level arcing currents. And take a look at where all these specific arcing currents need to fuse, as well as where they move off to the left, as well as where they clear. 0.163 is noted over here, 0.058 down here, as well as 0.199 on the top. This is a 2500 amp current limiting fuse, A4BQ. Notice the instant energy, 6.3 calories per centimeter squared, 3.2 calories per centimeter squared, as well as 15.4 calories per centimeter squared, which is 2.4 times higher than it was before. Again, this is a cautionary level because after 8 calories per centimeter squared, then you would receive a third-degree burn if you're not wearing any specific PPE. Now, let's move on to part 3. You increase the transformer size again. Here are the outputs, again, pasted individually for the 3 scenarios run. 58.196 for all 3 voltage fault levels. For the arcing fault, VCBB calculates it at 28.868. VCBB next is 33.474, as well as HCB is at 28.085. Again, notice where the varying level arcing currents clear this specific arcing fault at these specific time periods. This is a 3000 amp fuse, A4BQ. This is what I'm specifying in this case. Again, notice the incident energy, 20 calories per centimeter squared, 11.7 calories per centimeter squared, as well as 47.3. Now, we have labeled this as a danger because we want to make sure that people are understanding the differences in the 2018 model versus the 2002 model. And again, all of my assumptions are labeled here at the bottom of this slide. So remember that PPE, personal protection equipment, is the least effective in this case, since there is 2.4 times or 240% more energy than there is in the 2002 model. It has been noted in several recent IEEE presentations that maintenance personnel have been recorded not wearing enough PPE during an arc flash event. Most employers adopt a 40 calorie per centimeter squared as the upper threshold. If there was a fault and in this application no PPE is worn, then the 0.609 second clearing time could potentially and probably would be lethal to the worker if exposed at 24-inch working distance if horizontal electrodes inside a metal enclosure are present. Next, taking a look at a 2500 kVA transformer based upon the 1584-2018 method. These, again, 3 scenarios pasted with an EasyPower. Bus bolt default at 58.291. Arcing fault is at 32.95. 33.501 as 32.603. These are the individual values. Notice that EasyPower within the short circuit options, the 1584-2018 model has a maximum clearing time of 2 seconds, which I'm noting right here. This is a 4000 amp class L A4BQ fuse. Notice the instant energies at 87.2, 103.6, as well as 181.2. Again, something similar that you've seen before, for 2.1 times than it was calculated in 2002. Part 5, the only thing I'm changing here is 2 parts. I'm changing the working distance as mentioned in the agenda. Parts 1 through 4 are 24-inch working distance. And you expect once the change the working distance from 24 inches as well as to 18 inches at the arc flash instant energy and will go up, and it has. But also, in this case, if you do have the secondary full load amps calculated for this type of transformer, the secondary fuse design range for the NEC 450.3 overcurrent protection article will be towards the minimum at 3500 amps, which I'm specifying in the lower right-hand side. In summary, let's take a look at this and the results. But we're listing the 18-inch working distance. The bus bolt default is 58.291, as well as the arcing faults associated with 28.888, 33.501, as well as 28.105, as well as the clearing times associated with these class L fuses. Instant energy, 121.94, as well as 278.6, 2 times higher than it was calculated in 2002. So in summary, since there are problems associated with varying cable lengths as well as varying transformer sizes, let's take a look at the code on page 161 as well as 162. You notice informational note number 3, talking about this specific article. IEEE 1584 does not distinguish between 2002 as well as 2018. So maybe you should take a look at 2002. You should take a look at 2018. You should take a look at both, which is why we've included them in this presentation. 2017 National Electrical Code 240.67. This is the article as it reads in the book. 240.67 arc energy reduction, where fuses rated 1200 amps or higher are installed. 240.67 A and B shall apply, and this requirement shall become effective January 1st, 2020. A, for documentation for the paragraph, reads that documentation shall be available to those authorized to design, install, operate, or inspect the installation as to the location of the fuses. Paragraph B, method to reduce the clearing time. You shall have a clearing time of 0.07 seconds or less at the available arcing current, or one of the following shall be provided. Method B1 is differential relaying. B2, energy reducing maintenance switching with local status indicator. B3, energy reducing active arc flash mitigation system, or B4, approved equivalent means. Again, this presentation is talking about both, and we'll be discussing how we mitigate and solve these arcing current clearing time problems for fuses. Let's discuss as well as start to begin to model these solutions for 15 kV and below applications, as well as taking a look at the engineering control methods for the 2017 NEC that would affect the NFPA arc flash label. Let's look at the EasyPower modeling solutions for 15 kV and below applications. This slide is talking about the introduction of the new generation HPC switch, as well as the protection details. This example is a fuse composite time current curve where you will introduce how this device is a solution for the code. Progressing through this device, as well as how this class L fuse is attached, as well as help you understanding the components of this device. The green area of the time current curve is where you always have fuse protection. Notice on the right hand side, I'm highlighting in green as well as in blue how the different components are applicable to the time current curve. In this section, the fuse and instantaneous combined protection are provided, as well as taking a look at how this instantaneous relay, this low voltage instantaneous relay, has a protection time period of 58 milliseconds. The NEC has provided the 0.07 second line, which is documented within this slide. And at the bottom, you will always have fuse protection. So the core of this device is an insulated case circuit breaker with the low voltage relay opening within the main contacts similar to a circuit breaker design, measuring amperage time in the instantaneous portion of the time current curve, clearing low voltage arcing faults or fuses. When you include the full range of available overcurrents in this always fuse protection area of the time current curve, it allows for coordination and selective coordination for all levels of arcing currents. This device clears arcing faults within 0.058 seconds or 3.5 cycles, which is a solution that we are looking for. This device was introduced by GE Industrial Solutions, which was sold to ABB, headquartered in Zurich, Switzerland, a global leader in electrical equipment technology. The divestment of GE Industrial Solutions from the General Electric Company received worldwide regulatory approval on June 30, 2018, and as of July 1st, 2018, this new generation HPC switch, which is a UL, or Underwriters Laboratory, 977 device, is now manufactured by ABB. The new generation HPC basic application for 240.67, meaning the code for 0.07 seconds or less. The values that I pasted in this slide are the exact same what I had before for a 3000 amp main fuse, but now, as I mentioned before, it's good to take a look at what was calculated in 2002, since on page 162 of the NEC code, it does not distinguish between 1584-2002 as well as 2018. So let's talk about both. BCB, the bus arcing fault here is shown at 23.21 or 40%. And now with the 2018 method, all arcing faults are included here at this slide. Now, the composite curve is added here for the green line, which is added for clarity. Where the arcing fault clears this specific device, it clears at a time of 58 milliseconds. So this new generation HPC can be set to meet the 2017 NEC Article 240.67, paragraph B. When modeling this specific device, we are now going to apply it to our 3000 amp 480 volt application with a setting of 6.5. Notice I still have my 2002 method as well as the 2018 method labeled here. On the left-hand side, I have my phase trip as well as the instantaneous pull-down menu selected here at 6.5, but notice that the instantaneous pull-down menu allows the composite time current curve to be shifted from the left to the right, as well as being set to 2.0 all the way up to 10.0, depending upon the amperage of this device. On the next slide, nothing has changed, but I'll tell you a little bit more about the details of the graphics. But again, the outputs of this in EasyPower at the bottom right-hand portion of the screen, it clears it at 0.058 seconds. Again, this is a solution that we're looking for. Now, when we're talking about transitioning into the next section of the solution for 240.67B1 differential relay, there are 5 types of main transformer fault types: face-to-face faults, three-phase faults, ground faults, core faults, as well as tank faults. Under a no-fault condition, if you take a look in the center portion of this slide, if you have current entering into a zone as well as current leaving the zone, if it's equal to 0, then you don't have a fault, which means you are still protected. Taking a look at a fault condition where you have current as well as I1 plus I2 greater than 0, well, now you have a fault condition. But if this is the case, then something would be protected. Under a transformer differential protection, 87T compares the current going into the transformer zone versus the current leaving the transformer zone. Carl Smith from ABB, with his professional engineering license, he performed an EasyPower webinar, and it is listed here at the bottom of this slide, which you'll receive as a PDF towards the later portion of this presentation. When taking a look at transformer differential relays as well as a magnetically actuated circuit breaker, for this portion of it, the RET615 relay features a 3-phase transformer differential protection, including optional peak-to-peak differential for faster clearing time. With the EasyPower model that I will demonstrate later, I've added the mini voltage circuit breaker timing, the protective relay differential protection timing, as well as the protective relay contact timing equaling 0.073 seconds, which is conservative and it could be faster depending upon the options chosen. Moving to the right with a modern circuit breaker, this AMBAC circuit breaker has the embedded vacuum interrupters, the magnetic actuator driver for improved reliability, increased safety, as well as reduced maintenance. With the easy installation as well as reduced cost of total ownership, you eliminate dust, dirt, as well as the condensation within this specific type of circuit breaker. So since you have a reduction in maintenance, that means personnel would have a much less risk of maintaining a circuit breaker like this type, and they don't have to be exposed to the arc flash hazard as often, which is a great NFPA 70E method for what Samy mentioned before, for substitution, as you are replacing the hazard with a proper design, which allows for lessening of a hazard by spending less time working in the switchgear. Every person understands that if there's less maintenance, less work, leading to maintenance personnel returning home and being safe. Next, B2, the introduction of fused maintenance switching for 240.67B2. This is a second instantaneous setting on the low voltage relay. It may be set from a minimum of 1.5 to the same 10.0 maximum for the normal instantaneous. The RELT maximum clearing time is 0.05 seconds or 15 milliseconds. The local control switch provides feedback, which is listed on the right-hand side, about the blue LED switch. When this is activated or turned on, the command has been received as well as processed. This is intended for temporary activation while a worker performs a task in the arc flash boundary. To make it clear, this does not influence the NFPA 70E arc flash label. When modeling the fused energy reducing maintenance switching, or ERMS, this low voltage main device with the RELT, again, I'm labeling this on the left-hand side, but if you were to paste this with an EasyPower, you were to go into maintenance mode, turn it on, which I'll perform with you live a little bit later. But take a look at the same arcing faults, bolt faults, as well as the varying level arcing currents that I documented before. The only thing I'm changing is just turning the RELT on, but also labeling this with, instead of a 6.5, at 4.0. Remember that you want to set your protection off to the left so that you always have a clearing time if there is an incident at 0.05 seconds. Again, this is a solution that we are looking for. All my assumptions are labeled at the bottom. Working distance of 18 inches, bus electro gap, as well as electrical configurations, as well as the switchboard dimensions. Now, talking about the solution to case number 1. If you do have this device with HPC2, it clears it at 0.058 seconds, or in this case, where I've activated RELT in all the cases. So individually, I'm pasting all 3 types of electrical configurations, one by one by one. BCB is shown here for all these types of 1200 amp fuses, with the cable length of 300, 600, 900, 1200, as well as 1500 feet. Again, in the center is VCBB, and at the bottom is HCB. We've labeled both of these as a temporary situation because 1.3 calories per centimeter squared is labeled right here, as well as 3.2 calories per centimeter squared is labeled right down here. Again, it is recommended for the 1584-2018 guide that you utilize the most conservative and highest arc flash value within the system. So 3.2 is a potential value that would be seen, but again, this does not influence the NFPA 70E label. But taking a look at what meets the code requirement, if you do have the instantaneous ordered with this specific device, then you would always see 0.058 seconds. But in this case, we are labeling at 0.05 seconds, and all three scenarios meet the intent of the code requirement, which yields the goal of arc energy reduction for fuses. When modeling the fuse instantaneous settings for 240.67B and B2, left-hand side is the low voltage breaker data within the specifications. As mentioned before, this is the insulated case circuit breaker. Moving off to the center under the phase strip, the instantaneous setting is set right here for 240.67B, as well as the rel feature for 240.67B2. Off to the right, you choose your fuse or what is recommended by the manufacturer. Again, this applies to 600 volts, 40 volts, as well as 208 volts. Summary: to achieve constant lower levels of arc flash instant energy with this device that reflects the NFPA 70E label, the instantaneous feature of 240.67B must be included with the Class L fuse off to the right. Otherwise, you do have the code option of choosing 240.67B2, which will not affect the NFPA 70E label. So in summary, B and B2 can be combined together with this device. Next, we will introduce the energy reducing active arc flash mitigation system. With this, I'll briefly discuss this type of solution as well as this method, and then I'll go into the live version of EasyPower and show you 240.67 solutions for new installations as well as retrofits for B, B1, B2, as well as B3. In this example, the REA 101 relay, again, if you take a look at the bottom portion of this slide, you'll see the webinar link for where Carl Smith performed a previous webinar with EasyPower. So let's talk about this and how this technology works. If there is an arc and a cable compartment, taking a look at a feeder here, taking a look at this green feeder, this green circuit breaker down here, if there is this little electrical bolt, that would create an arc, and both relays, the REA 101 as well as the REA 105, would detect the light, and both relays detect the overcurrent. Both relays send the current information to all connected units. That's why everything is connected together with all the red squiggly lines as well as the green squiggly lines, as well as the purple connections between the two REA 101 relays. Only the affected feeder breaker is open, which will allow for coordination, selective coordination of this specific system. Now, with this information, let me go into the live model of what I have understood within EasyPower in order to take a look at the solutions and demonstrate what you could see within the specific system. So these are solutions by the book. And what I will be discussing as well as modeling for you, these are arc energy reduction solutions. There's actually some verbiage that's carried over to circuit breakers, but I'll talk and walk around the system with different cable lengths, transformer sizes, medium voltage bus differential, and taking a look at how I'm specifying the CTs for bus differential, as well as talking about the arc flash relay or the UFIS device that is a technology in order to meet the code. So let's talk about a new substation protection and control at the bottom. As mentioned before, in case number 1, where we have problems with current limiting fuses, and if you have different arc and current clearing time problems, a different way would to be take a look at technology. Otherwise, you'd be limited to the cable length. So let's take a look at, if I go to short circuit, making sure that my short circuit options have 1584-2018, and it is. I'll go to apply, and I've already pre-labeled this with VCB, VCBB, as well as HCB. If I run arc flash, and again, I will work in a clockwise fashion around the system. So let's start with case number 1, where we had problems with varying cable lengths for this scenario. So with a 300-foot cable with a current limiting fuse, 5.7 calories per centimeter squared, or with a 600-foot cable run, I had 14.2 calories per centimeter squared. Versus the solution, in order to meet the code, as previously mentioned in the slide, 1.6 calories per centimeter squared is labeled, and I will toggle on what the maintenance mode will do and what happens when I turn it off. So once I have this specific device, again, this is a UL listed device, NEMA, as well as available for new and retrofit up to 200 KA. So I'll zoom in just a little bit closer so you can see by the book method how we want to affect the arc flash label, even incrementally more. So instead of 1.6 for the maintenance mode, I'm going to put on the maintenance mode for B2. So instead of 1.6, you would have a lower level of arc flash incident energy of 1.3. So I'm going to turn it back off because this is the device that meets the code requirement for 240.67 paragraph B at 1.6. So notice there is an IEEE white paper associated with this device called Improving Selectivity for Arc Flash Protection Through Optimized Instantaneous Protection Settings. Well, so by the book, 2017 NEC article 240.67 B as well as B2, which I've demonstrated here. And B2 is equal to the 240.87 paragraph for circuit breakers. So notice that 1.6 is exactly what I have over here on the left-hand side. I will run a little bit later in the second scenario what HCB is, but let's move around the system in a clockwise fashion. Over here, the 240.67 code, which you have, take a look in the solutions for varying transformer sizes. Again, I have a 2500 kVA transformer within the system, and I wanted to affect this label right here. Notice that my 4.0 is exactly what I'm showing right here at 4.0 calories per centimeter squared. I will mention to the audience that once you put this in the HCB electrode orientation, it goes much higher. Again, I'll run that as a case a little bit later. Let's move on to B1, differential relaying. Differential relaying is equal to the 240.87 article B2. So right here, I have a label of 2.4 calories per centimeter squared, which is exactly what is a solution by the book. So this is how you can affect the label for solution 240.67 B1 as well as 240.87 B2 as well. Now let's take a look at, when you're taking a look at specifying relays, there's multiple relay manufacturers out there. This specific example is one of the solutions for the code, which you'll have to consider, but also taking a look at the CTs that I would be specifying. Now there's actually a couple different types of CTs or ways to understand the specific advantages of the next phase of evolution by design with digital switchgear. What I'm going to be talking about next is a Rogowski coil. Again, when specifying the CTs for a differential relay, you can use traditional CTs or you can take a look at Rogowski coils. Now there are several advantages of Rogowski coils, converting the analog voltage as well as the current information into digital and voltage information. With these Rogowski coils, it eliminates ferroresonance and the danger with sensors. So these specific Rogowski coils are based upon not having the large ferromagnetic path, which is associated with the core. Also, there are less internal heating elements associated with this type of Rogowski coil. Notice that I have phase A, B, as well as C indicated here with this specific types of Rogowski coils. Again, this is the IEEE paper. If you'd like to download it, it's the next phase in the evolution of safety by design for digital switchgear. And that's what I'm specifying for my CT up here. So if you have any questions on that, feel free to let us know. Now moving around the system in a clockwise fashion, let's take a look at how we affect it within a feeder or within the transformer zone, within a transformer primary installation. So this device, again, what we want to do is affect the arc flash label. This is 240.67 B3, energy reducing active arc flash mitigation system, which is equal to B3, 240.87 B4, energy reducing active arc flash mitigation system. In this scenario, notice that I do have extremely low levels of calories per centimeter squared, but something similar to before, 2.0 times higher than it was calculated in 2002. So these are the methods within a 15 kV new application for substation protection and control. Now what I'm going to do is introduce the HCB electrode orientation. So I will show you what I've pre-labeled within these buses, as we will take a look at the solutions by the book, but also taking a look at changing this from VCB to HCB. The working distance is specified at 18 inches, electrical gap at 25 millimeters, as well as the electrical configuration changing from VCB to HCB as the worst case scenario. Enclosure size is documented here. Next, I will go into the next portion of where I want to take a look at solutions from VCB to HCB, changing the electrode orientation on the bus. Differential relay, arc flash hazard, changing it to VCB as well as HCB. Notice as I had before, this is my 87T relay, specifying the 87 relay function at 0.073 seconds. Finally, I'm going to change the electrode orientation for the V3 method for 240.67 code from VCB to HCB. And I'll show you the results that I've already computed, but they should match exactly what I have here as well. Arc fault. Okay. Now taking a look at the pre-labeling I've completed for this specific example, again, walking around the system the second time. 3.8 calories per centimeter squared matches exactly what I have here, which is 2.4 times higher than it was in 2002. Let's work clockwise within the system. Notice that I have cautionary labels at different areas within the system. So again, right here, so instead of 4.0, which we were calculating before, HCB calculates at 9.3 calories per centimeter squared. This is a different type of protection suit, so make sure that you wear your PPE appropriately. So again, this is 2.4 times higher than it was in VCB. Differential relay, 240.67 B1 as well as B2 for circuit breakers. Same thing. 4.5 calories per centimeter squared, which matches what I have over here. So it's 1.9 times higher than it was in 2002. Now, taking a look at the system, again, these specific CTs as well as, or if you like to use Rogowski coils, is up to the customer. Taking a look at the specific bus here for the RE105 as well as the UFIS device, as well as the 101 UFIS device contained within the transformer primary installation. Again, this is an IEEE paper. Samy Faried actually published this paper. It's called Arc Flash, the New Regulations as well as Advantages of the Ultra-Fast Current Switch. Notice that in 2.0 VCB is 2 times higher than it was calculated in the original condition. So in terms of solutions, there are many types of solutions out there from multiple vendors for many types of transformer differential relays. This specific example, it can be utilized in switchgear for a truck installation, side installation, top of box installation, or in the back of switchgear. If you're taking a look at the transformer primary installation, it can be located within a transformer zone, which is located here. Zoom out a little bit. So these are these solutions for 15 kV and below new substations. But let's take a look at a retrofit application as well. Now I'm going to deactivate this entire section. And I'm going to move on to the right to my retrofit application. Again, these will be by the book. I'll just run one to help you understand a retrofit scenario. Activate this. And then make sure that this is in the VCB electrode arrangement first. And then I'll begin to run my short circuit, both the buses. I'll zoom in a little bit to the transformer retrofit, meeting the code requirement for 240.67B3. Again, it's equal to 240.87. VCB is calculated at 0.4, which I'll zoom in a little bit. This is how we affect the inside of a transformer zone and provide that solution for 240.67B3. When specifying this specific device, notice that you go into arc flash hazard. This is the device I'm using. It is a specific relay function as well as the clearing time of 0.004 seconds or 4 milliseconds. Now let's change the electrode orientation from VCB to HCB and see what happens. So again, I've pre-labeled this. So probably a value that which would probably be realistic within the field. after 2018 is included for the most extreme case. So over here, I've labeled this as 0.9 calories per centimeter squared, which matches the output of what EasyPower models here at the bottom. 0.9 calories per centimeter squared, which is 2.3 times still higher than it was calculated in 2002. So in retrofit applications, there are many types of solutions from multiple manufacturers. If there are fused load interrupter switches with circuit breakers, and if you want to have a differential relay, meaning the intention of 240.67B1 or 240.87B1, it's the same. Again, there are many types of manufacturers having UL listed equipment as well as ANSI rated relays, protected relays. Now working within a system, like I mentioned before, within a transformer retrofit, this is this paper that Samy published, Arc Flash, new regulations and the advantages of the ultra-fast grounding switch. It is available for public download. Taking a look at the bottom, if you take a look at what we mentioned before of how to affect the arc flash label for varying cable lengths, if there are specific existing HPC devices out in the field, which are UL and Canadian UL listed, NEMA as well as UL 891 switchboards. This specific device is again an IEEE paper, which can be retrofitted for 200 kA max applications. Again, by the book, it meets a method for 240.67B as well as B2. Now that I've provided a detailed analysis of EasyPower, completing 15 kV and below retrofit fused substations as well as 15 kV and below new substations protection and control, these are the specific inputs that the designer, the electrical engineer of record, as well as an end user needs to consider when performing these new equations. It is very detailed. Moving back to the presentation. Modeling the settings. For 240.67B3, the energy reducing active arc flash mitigation system, this is where the UFS device, so the ultra fast earthing system, is capable of continuous protection, where no user intervention is necessary. So this provides engineering control. It can influence the NFPA 70E arc flash label and be completely selective with overcurrent protection. It is extremely sensitive with well-placed sensors for light detection. Extremely rapid arc quenching time for arc resistant qualities using the standard equipment enclosures. And on the right-hand side is taking a look at the relay for the specific manufacturer as well as the type for 240.67B3, as well as how the REA 101 is labeled on the right-hand side. And this is a webinar that was performed by Carl Smith from ABB, which is available publicly. Next, taking a look at the modeling settings for B3 in the specific application. Just like I clicked on the specific bus for the transformer application, again, it's just pasted for this specific scenario. Application for circuit breakers as well as for fuses is very important to understand the applications of this specific device, as it operates at fast at 4 milliseconds in these specific scenarios. We recommend the applications to be utilized within circuit breakers within medium voltage, within a transformer zone, as well as low voltage. Just make sure you contact the manufacturer for proper placement, as well as make sure that the instructions are followed exactly. The fuses on the right-hand side for the application for 2017 NEC 240.67B3, this is where you can have the UFS device labeled within the medium voltage area, within the transformer zone, but also please notice that for low voltage, please see the factory, otherwise see solution 240.67 paragraph B or solution 240.67B2. This is where the UFS device is located within this specific area. And the reasons why we can't use a low voltage fuse, because it needs a fuse to be relatively small. So this could be potentially a scenario where you see a bolted fault much faster with a class L fuse. If you remember early in the presentation, the 1400 amp fuse in the 1000 kVA transformer example, the arc flash instant energy was shown to be low, which didn't show a need for this specific type of device. The arc and fault currents are not high enough to melt a low voltage fuse in the current limiting range in most cases, unless you have very, very low impedance on the transformers and high medium voltage fault current. So this is why we are documenting for low voltage applications. See the factory 240.67B or solution 240.67B2. So on the right-hand side, again, we are labeling the clearing time in seconds, which is required by law per the 2017 NEC. And feel free to click at this link at the bottom in order to understand the EasyPower webinar from Carl Smith. Now, I'll thank you very much for your time and attention to the details. Now, please allow me to turn the presentation over to Samy to offer additional information, and he will conclude the presentation.
Thank you, Ryan. I'm sure everybody got a good dose of alternative solutions. What I'm planning to do is go through the details of the UFIS application. If I may remind you, we talked about the arc energy equation equals volts times amps times time. The UFIS is used to drive the voltage to 0. And if you put value of 0 for the arc energy, you're obviously going to have a 0 energy, which means the arc immediately is extinguished. There are some other methods that we're not going to go through it now, which is controls the current, and the electronically triggered current limiter is an excellent solution for this. So if I may remind you of the arc energy equation, volts times current times time. Now we are controlling the voltage. The components, as you see from this slide, the components of the UFIS consist of a fiber optic around the switch gear arrangement, and you have the option of surrounding the entire bus system with a fiber optic or individual cells that can be placed in critical feeder compartments. Once the fiber optic, once an arc flash occurs, the fiber optic will carry the signal into a light detection relay, REA 101, and this will translate it to a signal that will be sent to the electronics activating the tripping element of UFIS. So I sense the arc, I send it to a light detection relay. Light detection relay will send a signal to the electronics of the tripping element, and finally the electronics will signal the tripping element to trip. I'm going to show you the details of the tripping element. Go ahead, please. Okay, here is the tripping element. To your left, we're assuming one of the phases, like phase A, B, or C. And the one to the left shows normal operation. I mean, nothing is happening in the system. If I may pay your attention, this is phase A, and down here there is a piston that can be activated using the red gas generator in the bottom. That red gas generator is good for 15 years with no maintenance. Once we sense an arc, the gas generator will be activated, and consequently will go to the right-hand side and will be pushing the piston in order to contact the phase to ground. If you take a close look at this model on your right-hand side, you'll see the piston is attached to the phase and also ground. So that's the operation of the tripping element itself, which means under normal condition, nothing is happening. When you have an arc, then all the three phases will go down to 0. And if we go back to the arc energy equation, putting a value of 0 for the volts, the entire arc energy will go down to 0. Okay, so what's happening then is the following. There are two phases to the function of the UFIS system. The first phase is grounding the phases, and that will result into an energy of 0, which immediately extinguish the arc. The second phase of this is the normal protective system, which will take over and will be tripping based on 3-line to ground fault. So those are the 2 phases of operation of the UFIS: detecting the fault, extinguishing the arc, and then the normal protective system will take over. The UFIS can be very nicely fitted inside, on top of the switchgear, and or in one of the, as you see in the upper left right hand corner, it can be inserted or installed in a compartment in the switchgear or the MCC or whatever distribution element you're using, or can back on top here. Following slide, please. Okay, I hope the system is going to be working. To your left is a system which has no UFIS. To your right, you will see a system which has the application. Let's give it a try, Ryan. See if this is going to work. If you activate the animation, please. Nope. It's not working. Okay. Without applying the UFIS, you'll find flames and tremendous destruction of the unit because of the arc flash. And if I may count the consequences, number 1, the workers may be exposed to serious injury or death. Number 2, I may be destroying the equipment. And number 3, I am causing an outage. That's in the system before. The system after applying the UFIS, you will only notice a puff of smoke. So I saved the worker lives. I also saved the equipment from serious damage. And thirdly, I am minimizing the outage. Outage can be translated in a medium-sized pulp and paper plant. Each hour is ranging, power loss would equate to about $100,000 of revenue loss. Okay, let's go following one, please. Okay, so what are we gaining? Number 1, we are gaining a definite solution which extinguishes the arc within 4 milliseconds, and thereby achieving probably the highest level of safety for the worker. It's very easily installed. It can be applied to motor control center, low voltage switchgear, medium voltage switchgear, and the 4 millisecond is a key element here in evaluating the arcing current and also the incident energy. So the UFIS can satisfy definitely the 240.67 B3, but more importantly, it's a definitive solution for arc flash. You don't have to guess. As I mentioned in the beginning of the presentation, we are dealing with empirical formulas, which means it gives you an approximate value of the incident energy, but with the UFIS, you're dealing with an exact formula, which can bring the voltage down to 0, and consequently, it will extinguish the arc and cause the maximum level of safety for the worker. Okay, we go over the applicability. Next slide, please. Applicability of the NEC. Go ahead. As you notice from the map slide, that some states take into effect the NEC as it comes out, and some states take them a while to rise to the occasion. So this is to remind all of us that regulations are great, but safety in the field depend on your experience, depend on exact equations to apply. I mean, basically, you don't have to guess when you're using a technology like UFIS whether you have protection or not, but you have to guess when you are not absolutely certain of the value of the incident energy, and also if you have applied the NEC or not. So let me summarize the whole situation now, if I may. Next slide, please. Okay, we have three regulators. We have OSHA, we have NFPA 70E, and we have IEEE 1584. Those are, by the way, the major ones, not the minor ones. And we have empirical formula that, if you look at the table shown, that will indicate the clearing time and that will comply with the 24067. And also, we have to be aware, extremely aware, of technologies available in the market, including the voltage killing machine, which is the UFIS, and also there are, on the current side, there are electronically triggered current limiter that can also affect immediately the value of incident energy and minimize the hazard to the worker. But above all, nothing will replace a good experienced eye looking at the site condition and determining what is the safest procedure to proceed with. The most important thing in this message is life cannot be replaced, and therefore you have to be meticulous in looking at different options you are using and how effective they are, and also introduce technologies that are exact and use exact equation. I'm honored and delighted that you shared your time with me, and we'll switch back to Jim, I believe, for questions and answers.
Thank you very much. Yeah, we do have some questions here that let me read, and Ryan or Samy, you can answer as you see fit. Question came in from Rajat, and that is, can we perform a test to measure the time actually is less than 4 milliseconds on site for the UFIS?
The matter of fact, I'm going to take care of this. We actually went to KEMA, which is an outfit specialized in testing electrical power systems, and we used the current limiting fuse and the UFIS, and we actually measured less than 4 milliseconds of clearing time. Not only that, but we also measured the incident energy before applying UFIS, and then we did another test for after applying UFIS, and we dropped from 49.8 calories per centimeter square down to 0.4 calories, even less than half a calorie per centimeter square. A definite solution, very accurate solution. Excellent question.
And then one other one regarding EasyPower specifically. Sreet is asking, how do you model the RE105 relay with optical sensors in EasyPower? And we've actually demonstrated this in the video with Carl Sreet, and it turns out the way, since EasyPower can't simulate the light sensor, you set up the downstream bus, which is being protected by that relay, with a maximum time after the fault, and the time delay is dependent upon the reaction time of the sensor and the relay itself. And so you'd set it up for a fixed time, and that's what's used in instant energy calculations. I think, let's see. Here's another one from Renato. Have all the available equipment addressed here been added to the EasyPower database for use in the tools today? I believe that is the case. In fact, I don't recall that we've talked about anything. Ryan, is there anything missing as far as you know, as far as the library?
No, I'll walk through B, B1, B2, as well as B3. In terms of B, there are varying cable lengths that the designer has, the current limiting option, and there's new equations associated with the new model. So the current limiting options are available when you model a specific fuse. Again, contacting many different manufacturers for that specific method. Now, talking about the HVC2, that is fully integrated within the EasyPower software program. meeting B as well as paragraph B2. When I toggle the EasyPower control method for turning it on as well as turning it off, those are completely compliant with how EasyPower models the specific scenarios for in a permanent condition as well as in a temporary condition. Talking about B1 differential relaying, all the differential relaying are in there. Again, Carl from ABB provided a 1-hour webinar on how to specify and take a look at the EasyPower menus. So that's completely compliant with what is required for the designer. And then talking about B2, as mentioned before, the HP2 switch with the route feature, once you turn it on, it meets the intent of the code, but again, it does not influence the NFPA 70E label. B3 for the UFS device, the arc flash relay that Samy was mentioning in the application, what I modeled before, yes, that device is within the pull-down menu, and the ABB REA 101 is available from EasyPower. So yes to 240.67 B, B1, B2, as well as B3.
Thank you.
Good question. Good question.
Jeff has a question that I'm curious to see how Samy's going to answer it, and that is, how do you decipher the specific applicable electrode configuration for each piece of equipment to obtain accurate incident energy level?
Look at it. In most cases, you will be able to see, I assume that you want to see the configuration of the electrodes. If this is the question, is if you have access to it, great. If not, the manufacturer information. And then if not, unfortunately, we have to go to worst case scenario, assuming horizontal and exposed to exposing the worker's face and chest to it. I hope I answered the question.
I think you did. And I would add, Jeff, make sure you document whatever assumptions you use, just so that it can be followed up by anyone, looking at your report later on.
Also, so you don't get arrested.
And so there's one follow-up question about the UFS. I think this will be the last one we have time for, and that is there a limit to the number of operations for the UFS?
The cartridge must be replaced. Each time there is the cartridge, which include the tripping units, this must be changed, and it takes probably less than an hour in the field. We give you spare parts for the UFS components.
I apologize. There is one follow-up question regarding the electrode configuration, and that is, if the equipment has both vertical and horizontal bus in the area, which would you select? Now, I guess let me jump in there. I would offer EasyPower allows you to select both if you judge that either is a possibility inside the compartment, and consequently would produce an answer that's considered to take into account whichever is worst case for that particular situation. Samy, do you have any comments on that? I'm sorry, Ryan.
Well, yeah, after reading, I think it's several hundred pages of the guide. I believe it's around over 100. But it does document in the guide, and I did highlight it, that it does list a minimum of 2 electrode orientations that you have to pick. So you definitely want to take a look at what's worst case scenario for arc flash incident energy. In most cases, what we presented, HCB is the worst case scenario, but you also need to be concerned about the other aspect of varying arcing currents, which would be associated with where the left-hand portion of the arcing current would be off to the left. Is it VCB? Is it VCBB? Or is it HCB? That is, unfortunately up to the United States to figure out. But it does list in the 1584 guide at least 2 minimum electrode orientations are to be analyzed.
All right, I thank everyone for attending. Ryan and Samy, thank you very much for your contribution. And we invite folks to attend our webinars, which we'll be following up through the rest of the year, both on Tuesday and Thursdays every other week. Thank you very much. Have a good day. Thank you, gentlemen.
Thank you.
Thank you, sir.